You know when your phone finishes your sentence, or a search engine just gets what you mean? Have you ever stopped to think about how that actually works? It all boils down to this really fascinating puzzle. How do you teach a machine, a thing of pure logic and numbers, the subtle, nuanced, and kind of messy meaning behind our language? Well, let's dive in and find out.
Right, so this is the absolute core of the problem. For us, it's totally obvious. A king and a queen, yeah, they're both royalty. A king and a cabbage, not so much. But a computer doesn't know what royalty is. It doesn't know what a vegetable is. It just sees text. So how in the world do we get it to go from seeing simple letters to understanding these complex relationships? So in the very beginning, people weren't even trying to get computers to understand language in a deep way. The goal was much simpler. Just find a way to turn words into numbers so a computer could count and categorize them. You can think of it as level 1, just treating words as simple, distinct items. The first big idea here was something called one-hot encoding. The easiest way to picture this is to imagine a gigantic switchboard, and I mean gigantic. Every single word in the dictionary has its own unique switch. And to represent a word, you just flip its personal switch to on, and make absolutely sure every other switch is turned off. So let's say you've got a super tiny vocabulary, right? Just 6 words. Dog might happen to be the first word. Its representation then becomes this simple list of numbers. A 1 in the first spot, meaning on, and then zeros for everything else. Super simple, right? Every word gets its own little spot, its own personal on switch. Yeah, but you can probably already see the massive flaw here. If your vocabulary is, say, 100,000 words, then each word is a list of 100,000 numbers with just a single 1 in it. But way more importantly, this method treats every single word as completely separate. To the computer, king is just as different from queen as it is from cabbage. There is absolutely zero concept of similarity. Okay, so attempt number 2, the bag of words model. And honestly, the name tells you pretty much everything you need to know. Imagine you take a sentence, throw all the words into a bag, shake it all up, and then you just count how many of each word you've got. The order, the grammar, all of that is just gone.
And this slide just lays it out perfectly. Look at the difference. With one-hot encoding, dog bites man is 3 separate ordered vectors. But with bag of words, it just becomes a single list that basically says, yep, I've got 1 dog, 1 bites, and 1 man. That's all it knows.
And that leads to a huge problem. I mean, dog bites man and man bites dog are, well, they're pretty different stories, right? But to a bag of words model, they look exactly the same. The real meaning, the context, it's all completely lost. We're still just counting items, and we're not getting any closer to actual understanding. So it became super clear that treating words like these isolated little items was a dead end. What was needed was a total revolution in thinking, a whole new philosophy for how to define what meaning even is. And this was the light bulb moment, the big idea, what people now call the distributional hypothesis. Instead of asking, what is this word? The new question became, where does this word live, and who are its neighbors? It's a really profound shift. Think about it this way. If I made up a word, let's say blorg, and you kept hearing me say things like, I ate a juicy blorg, or I need to peel this blorg, you'd start to get a pretty good sense of what a blorg is, right? Just from the words around it. That is the absolute core insight here. A word's meaning is defined by the company it keeps. Now, this new philosophy led to an incredibly powerful new technique. We stopped representing words as on-off switches, and instead started representing them as points in a complex, multidimensional space, a space where meaning literally has a location and where relationships can actually be measured. So here's the absolute key. We give every word a set of coordinates, a vector. But these coordinates aren't random. A neural network actually learns them by analyzing massive amounts of text. It learns to place words that appear in similar contexts, like king and queen, really close together in this space. And words like cabbage get placed way over on the other side of the map.
And this is where it just gets wild. Because these locations aren't just about how close words are to each other. The directions between words start to capture meaning. You can actually start to perform a kind of algebra on ideas. This is the classic example that just blew everyone's mind. If you take the coordinates for king and you mathematically subtract the coordinates for man, you're essentially removing the concept of maleness from royalty. Then when you add the coordinates for woman, you're adding the concept of femaleness back in. And the point in space you land on is incredibly close to the actual coordinates for queen. It's not magic, it's just math capturing these really abstract relationships.
Now, I know this might all seem like a really abstract idea, this whole multidimensional word space thing, but I promise you, this breakthrough is the engine running behind so much of the technology we use every single day.
I mean, this technology is the invisible engine behind modern search engines and those translation apps that feel like magic. And like this slide shows, it's also making a huge impact in really specialized fields like medicine, where it can analyze a doctor's notes to help suggest diagnosis. This fundamental shift in understanding language is truly everywhere.
And that brings us to the final thought, doesn't it? We started out just trying to turn words into numbers. We ended up creating these incredible maps of meaning, where concepts have direction and relationships. So the question becomes, if we can mathematically map the building blocks of our language, what does that mean for the future of understanding intelligence itself?